Okay class, welcome back. Today we are going to start our dive into some of the most useful math in chemistry. Today we are going to talk about moles. My objective for you today would be that you would be able to calculate how many moles are within a substance given the number of represented particles of that substance and vice versa. So, in saying this, let's dive into it. So when we get donuts, if we are wanting 12 donuts, we are not going to specifically ask for 12 donuts. Instead, we were going to say something like, let's get a dozen donuts, or I want a dozen of those donuts. Though a dozen does not technically represent a numerical value, it is understood to represent a specific quantity of a substance. We see this trend all throughout our everyday lives. For example, it is easier to sell paper by the ream opposed to individual sheets. A ream of paper represents 500 pieces of paper. If I'm trying to buy pencils for my students, it's more economical for me to buy by the gross opposed to the individual packages. A gross represents 144 of them. Chemists also have their own way of quantifying specific numbers of a substance. In order to find the relationship between the quantity of one substance and another, there needs to be a unit in which everything in chemistry can be converted to. This unit is a mole. A mole is the SI base unit used to measure the amount of a substance. A mole is abbreviated with the letter MOL. I know, helpful, right? So now we know a mole represents a certain amount of a substance. How do we figure out how much that certain amount is? Well, we're going to take how to figure out a certain amount of a substance in two routes in the next few lectures. The first route is how many particles are within 1 mole, and the second route we're going to figure out how many grams are within a mole. We're going to spend this video camping out with particles, and the next one camping out with masses. Through years of experimentation, it has been established that 1 mole of a substance is 6.022 times 10 to the 23rd representative particles of that substance. This is known as Avogadro's number, and you might as well commit this to memory because you're going to be using it a lot. Whether we are talking about a single element like copper, a molecular or covalent compound like water, or even an ionic compound like sodium chloride, 1 mole of that substance equals 6.022 times 10 to the 23rd representative particles of that substance. This brings up the question, what exactly are representative particles? Representative particles are just a generic cell encompassing the name that represents the number of particles within a substance. Technically, if we are talking about an individual substance, we are going to use the term atoms instead of particles. If we are wanting to represent a covalent or molecular compound, we would use molecules. And finally, if we were wanting to represent an ionic compound, we would use formula units. Yes, formula units can be abbreviated to FU, and this is the only time it is acceptable to use FU in chemistry. So whether we are talking about formula units, atoms, or molecules, Avogadro's number still doesn't change. We are going to have 6.022 times 10 to the 23rd representative particles in 1 mole of a substance. So in 1 mole of the ionic compound potassium oxide, there are 6.022 times 10 to the 23rd formula units of potassium oxide. Similarly, in 1 mole of carbon monoxide, there are 6.022 times 10 to the 23rd molecules in it. Just as we keep the example going for an individual element like lithium, there are 6.022 times 10 to the 23rd atoms of lithium represented in 1 mole of it. Okay. So now we have this ridiculous number drilled into your head. How are we going to use it? Well, in chemistry, you're going to either have to use a given number of moles of a substance and convert that into represented particles, or vice versa. We do this by putting what is given over 1 and multiplying it by the relationship of 1 mole of a substance over 6.022 times 10 to the 23rd particles of that substance, or its inverse. The way we know which relationship to use is by understanding what is given to us. In order for units to cancel out in chemistry, we must have the same unit present on the top of one relationship and the bottom of another relationship so they can cancel out. So, if we are given moles of a substance and we need to convert to representative particles of a substance, then we are going to use the relationship of 6.022 times 10 to the 23rd over 1 mole. If we're going from representative particles and trying to get to moles, then we're going to use the relationship of 1 mole over 6.022 times 10 to the 23rd particles. So let's work some practice problems for each of these types of problems. Suppose we are asked to calculate the number of representative particles present within 3.2 moles of calcium. First, we notice that we are talking about an individual element, so we're going to be using the unit atoms for our representative particles. Now, In order to work this problem, we are going to put what is given over 1, so 3.2 moles of calcium over 1. Yes, it is important to include the units now. You'll be thankful for this discipline later in the semester. Next, we are going to multiply by our relationship with Avogadro's number and moles. Since we started with moles on top in the first relationship, we are going to have it on the bottom of the second relationship so that it cancels out. So we are going to have to use a relationship of 6.022 times 10 to the 23rd atoms of calcium over 1 mole of calcium. Now we just cancel out units and multiply and divide. So moles cancel out, and 3.2 times 6.022 times 10 to the 23rd atoms gives us 1.93 times 10 to the 24th atoms of calcium over 1. In other words, we have 1.93 times 10 to the 24th atoms of calcium and 3.2 moles of calcium. Not too bad, right? Let's work another one. Let's say we were asked to calculate the number of represented particles in 12 moles of water. First thing that I'm seeing is water is a molecular compound, so our represented particles should be molecules. Next, I put what is given over 1, so 12 moles of water over 1, and I multiply it by the relationship of 6.022 times 10 to the 23rd molecules of water over 1 mole of water. This gives me that there are 7.23 times 10 to the 24th molecules of water in 12 moles of water. Okay, now let's solve some for moles if we are given represented particles. Let's take our water problem we just did and work it backwards. So a question may look like this. If we are given 7.23 times 10 to the 24th molecules of water, how many moles of it do we have? So we're going to put what we know over 1. So 7.23 times 10 to the 24th molecules of water over 1. Then we're going to multiply it by Avogadro's number relationship. So in order to cancel out units, we're going to have to put represented particles at the bottom and moles on top. We're going to multiply this by 1 mole of water over 6.022 times 10 to the 23rd molecules of water. This cancels out our molecules of water and leaves us with moles of water. Now all we do is simply multiply and divide out, and we get 12 moles of water in 7.23 times 10 to the 24th molecules of water. Okay, one last practice problem for today. Calculate how many moles are present within 9.03 times 10 to the 22nd represented particles of sodium chloride. Well, sodium chloride is an ionic compound, so our represented particles are going to be formula units. So I'm going to write what is given over 1. So 9.03 times 10 to the 22nd formula units of sodium chloride over 1. Then I'm going to multiply it by the relationship of 1 mole of sodium chloride over 6.022 times 10 to the 23rd formula units of sodium chloride. My formula units cancel out, and when I do the math, I get that there are 0.15 moles of sodium chloride present within 9.03 times 10 to the 22nd molecules of sodium chloride. Okay, I feel that this is a good place to stop for today. Remember, whether we are converting 2 moles or represent particles, we are going to have to use some form of the relationship between Avogadro's number and moles. In saying that, keep up the good work in the classroom, and see you next time.